Hello and welcome to the CompTIA Cybersecurity Analyst, CISA Plus, Certification Study Guide. In this video, we will discuss Chapter 2.3, Threat Actors and Actions and Types of Attacks. Please like, subscribe, and hit the notification bell. Types of attacks. There are a variety of different types of attacks that come from threat actors. Some of the most common include web server application attacks, remote code execution, data poisoning, and obfuscated links. A web server provides services that are implemented as web applications through software programs running on the server. A typical web application infrastructure is shown in Figure 2-5. The client's web browser makes a request using the Hypertext Transport Protocol Secure, HTTPS, to a web server, which may be connected to one or more web app servers. These application servers run the specific web apps, which in turn are directly connected to database servers on the internal network. Information from these database servers is retrieved and returned to the web server so that the information can be sent back to the user's web browser. A web application infrastructure is a tempting target for attackers for multiple reasons. A successful compromise could impact all web users who access the web server. An attack could provide a pathway into the enterprise's network infrastructure. The multiple elements in a web application infrastructure provide for a range of vulnerabilities that can be used as different attack vectors. Common web server application attack categories are request forgery and cross-site scripting attacks. In addition, directory traversal is another common attack. Request forgery. As its name suggests, a request forgery attack is a request that has been fabricated, a forgery. There are two types of request forgeries. These are a cross-site request forgery, CSRF, and a server-site request forgery, SSRF. Cross-site request forgery, or CSRF, takes advantage of an authentication token that a website sends to a user's web browser. If a user is currently authenticated on a website and is then tricked into loading another web page, the new page inherits the identity and privileges of the victim, who may then perform an undesired function on the attacker's behalf. In other words, in a CSRF attack, a request to a website is not from the authentic user, but is a forgery that involves crossing sites. Figure 2.6 illustrates a CSRF. Because a CSRF takes place on the client site, it is sometimes called a client-side request forgery. Server-side request forgery, or SSRF, takes advantage of a trusting relationship between web servers, as opposed to a CSRF, which manipulates the trust from a user's browser to a server. SSRF attacks exploit how a web server processes external information received from another server. Some web applications are designed to read information from or write information to a specific Uniform Resource Locator, or URL. If an attacker can modify that target URL, they can potentially extract sensitive information from the application or inject untrusted input into it. Table 2.2 outlines the differences between a CSRF and a SSRF. Attack name, attack target. Purpose of attack: CSRF user force target to take action for attacker while pretending to be authorized user. SSRF web server. Gain access to sensitive data or inject harmful data. Cross-site scripting. Most websites accept some type of user input such as visitor comments, web-based collaborations, search terms, and so on. The underlying web applications then use the input from users to create dynamic display content. For example, a user could enter Cengage into a search box, and then a web page displays back to the user, "You are searching for Cengage." Or a user could enter a new topic about a recent player trade on a sports web forum that would then be displayed to subsequent users who access that same topic in the forum. Threat actors can take advantage of this user input and display in a cross-site scripting, XSS attack. The term cross-site scripting refers to an attack using scripting that originates on one site, the web server, to impact another site, the user's computer. XSS is essentially a client-side code injection attack using a web application. An attacker attempts to execute malicious scripts in the victim's web browser, but not by directly injecting it into the user's web browser. Rather, the attacker inputs that malicious code on a website that accepts user input. The underlying web application that accepts the malicious code then becomes the vehicle to deliver the malicious script to every user's browser when they access that site. An XSS attack is shown in Figure 2.7. Malicious code in an XSS attack can be executed in the user's browser through VBScript, ActiveX, and even cascading style sheets, CSS. However, it is most commonly executed in JavaScript because this is fundamental to most browsing experiences. Although web browsers run JavaScript in a very tightly controlled environment with limited access to the OS and file system, it still has the potential to be misused by malware. In order for a threat actor to launch an XSS attack, the attacker must identify a web application that accepts user input without validating it, called sanitizing, and then uses that input in a response back to the user. There are three main types of XSS attacks. Name description comments reflected, XSS. A user enters input into a web application that is then immediately displayed back, reflected, to initiate the attack. The simplest form of XSS attack, persistent XSS. A threat actor enters input into a blog post or forum that is stored, persistent, and an unsuspecting user later displays it to initiate the attack, also called stored XSS or second-order XSS. Document Object Model XSS. A web application writes data to the document object model on the web server without proper sanitization, and the attacker can manipulate this data to include XSS content on the web page. The document object model is a convention used to represent and work with objects in an HTML document and other document types. A threat actor who controls a script that is executed in the victim's browser through XSS could fully compromise that user. The attacker can initiate interactions with other application users, including malicious attacks that appear to originate from the trusted victim, modify any information that the user is able to modify, perform any action within the application that the user can perform, view any information that the user is able to view. Web-based attacks frequently result in directory traversal. The root directory is a specific directory on a web server's file system, and users who access the server are usually restricted to the root directory and directories and files beneath the root directory, but they cannot access other directories. A directory traversal attack takes advantage of a vulnerability so that a user can move from the root directory to other restricted directories, viewing confidential files or entering commands to execute on the server. Remote code execution, RCE, occurs when a threat actor accesses a target device to make changes to it. Because this is done through a network connection instead of physically, that is, the threat actor is not sitting at the device making changes, it is called remote execution. Once threat actors have remotely accessed a device, the next step is typically to attempt a privilege escalation. Privilege escalation allows the attacker to gain illicit access to elevated rights or privileges beyond what is entitled for the user. Privilege escalation can be either horizontal, gaining access to rights of another account with similar privileges, or vertical, increasing the elevation of rights. Once elevated privileges have been attained, then threat actors use this ability to execute code, malware, on the device to make it under their control. Attackers can then exfiltrate data from that device, perform network reconnaissance, or launch other attacks such as denial of service, DOS, or ransomware attacks. The Log4j attack mentioned previously provided threat actors with RCE over devices. A Log4j feature allows users to enter custom code in a log message. The vulnerability in Log4j allowed threat actors to inject malicious code for the log messages that Log4j then processed as instructions. For hundreds of years, armies at war have resorted to well poisoning against their enemies. As its name implies, well poisoning is a malicious act to contaminate resources of potable water used for drinking and food preparation. Well poisoning has been used both offensively, as a terror tactic to disrupt and depopulate an area, and defensively, as a scorched earth tactic to deny an invading army sources of clean water. Rotting animal corpses have been thrown down wells to pollute the water, and in extreme cases, human corpses known to have died from deadly transmissible diseases, such as bubonic plague or tuberculosis, were used in well poisoning. In a similar fashion, threat actors use data poisoning to contaminate the data that is used in cybersecurity to identify an attack. For example, a defensive system can be used to detect unusual network traffic that could indicate suspicious activity. In a data poisoning attack, an attacker could slowly introduce their own fake data points seen as permissible activity in order to decrease the accuracy of the system. Over time, the system will eventually see the attacker's activity as permissible and will not flag it as suspicious. Data poisoning attacks have often been conducted against spam filters used by email providers. Email systems regularly detect advanced spammer groups trying to throw off email filters. This can be accomplished by the spammers reporting to the filters massive amounts of spam emails as not spam in large-scale attempts to skew the spam classifier. Another example involves online scanning services. Users can submit suspicious files to detect if they contain malware, as seen in Figure 2.8. Attackers have uploaded benign or harmless samples that have been falsely tagged by the threat actors as malicious. Anti-malware software vendors then download these results to update their own systems. However, the anti-malware software then reports these benign files as infected when in reality they are not, thus damaging the user's trust in the anti-malware even to the point of turning it off. Data poisoning is difficult to detect. The data models that are used to create attack profiles must periodically be retrained with newly collected data at certain intervals, depending on their intended use and their owner's preference. Since data poisoning usually happens over time through multiple training cycles, it can be detected when any prediction accuracy begins to shift. Obfuscated links. Not all attacks rely on technology vulnerabilities. In fact, most cyber attacks today rarely exploit a technology weakness as the initial first step. Instead, they start with social engineering. Social engineering is a means of eliciting information or convincing a user to take action that weakens security. Social engineering is almost always performed through deception and manipulation of the user. Because social engineering occurs through the exploitation of a person, it is sometimes said to be accomplished using human vectors as the attack surface. One reason most cybersecurity attacks are successful today is because they start with highly successful social engineering attacks, which then open the door for the next steps in the attack. It is estimated that cybercriminals use social engineering in 98% of their attacks. A growing trend in social engineering attacks is an attack that uses obfuscated links. To obfuscate is to render something obscure, unclear, or unintelligible. Threat actors craft deceptive URLs, which are the link addresses of a given resource on the web, to trick the user into thinking they are valid or secure links. There are several techniques for hiding the destination of URLs in a web browser so that an unsuspecting user does not know where a URL will actually redirect them. One of the simplest techniques is to use the HTML attribute, a href. The HTML code, your bank, instead of displaying attacker_site.com, will display your bank. Redirecting users to another resource or website but not displaying that destination URL in their web browser is known as stealth redirection. Another technique is to use a URL shortener. These online tools convert a longer URL to a shorter version. Because this shorter version gives no indication of the destination, threat actors often mask their websites with a URL shortener. Stealth redirection is commonly performed using an iframe tag or an Apache rewrite directive. While these techniques can hide a URL in a web browser, more advanced techniques are often used by threat actors to obfuscate URLs. There are three primary means by which obfuscated links are crafted today. Manipulate the @ symbol. The standard format of an HTTP URL is HTTP. Because no username, such as Anthonio in Anthonio@example.com, is allowed as part of a URL, when a browser interprets a URL with an @ symbol, it discards everything before the symbol, but then sends the request to the web resource following the @ symbol. The URL Google.com at 1157586936 treats google.com as a username and discards it, then sends the request to 1157586936, the Decimal Internet Protocol, IP, address of a web resource. Use alternative hostname formats. In the previous example, 1157586936 may generate suspicion since it is rare for a server IP address to be depicted as an integer. To obfuscate 1157586936 even more, it could be displayed in an alternative hostname format such as Google. com at 0xc0, 0xa8.0x0.0x1 hexadecimal, Google, com at 0300, 025000000001 octal or Google, com at 0300, 025000000001 mixed. By using obfuscated links, threat actors can create URLs such as your .bank.com at loginportal.onlinebanking.orly/loginportal.php to redirect unsuspecting users. Obfuscate with Punycode. Punycode is a representation of Unicode using the more limited American Standard Code for Information Interchange, ACII character subset. Punycode allows host names containing Unicode characters to be transcoded to ASCII. However, when transcoding characters from another alphabet, these unique characters may not be noticed. A recent attack using Punycode is shown in Figure 2.9. While the URL at first glance appears normal, upon closer inspection the letter K is actually a different character altogether of K cedilla, the 17th letter of the Latvian alphabet that appears in ASCII with a comma beneath it. This obfuscated URL, keepass.info, is completely different than the secure URL, keepass.info, and clicking it will redirect the user to an imposter website. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. We will see you on the next one.